Think back to the very first machine learning lecture you ever attended.
Oh boy, yeah.
Right. You were probably furiously trying to absorb every single concept. But, I mean, if I asked you today to repeat the exact sequence of words the professor used, you just couldn't do it.
No,
Your
absolutely.
brain didn't perform a lossless recall of that hour. Instead, you compressed the core intuition into your neural pathways. And, that compressed intuition is what actually helps you understand complex research papers today.
Yeah, which is, the biological process of discarding raw sensory data while updating internal synapses to retain semantic value. It's arguably the most efficient form of sequence modeling we know of. It is fundamentally a process of lossy compression over time.
Right, exactly. Which gives us the perfect conceptual lens for our mission today. So we are unpacking a paper titled End-to-End Test Time Training for Long Context.
Such a fascinating paper.
It really is. And this research brings together teams from Stanford, UC Berkeley, UCSD, the Astor Institute, and NVIDIA. We are going to rigorously analyze their novel architecture, which they call TTT-E2E.
Yeah, and they are moving past the usual architectural band-aids for long context scaling.
It's like sliding windows or sparse attention, things like that.
Exactly. And instead, they're reformulating the core sequence modeling problem as one of continual learning via meta-learning.
So let's set the stage a bit. The foundational motivation for this research stems from a very specific mathematical bottleneck, right? One that every practitioner working with large language models eventually hits.
Yeah, so in standard transformers, the self-attention mechanism operates in pseudodollar time complexity during the prefill phase. The KV cache effectively functions as that lossless recall you just mentioned.
Right, it stores everything perfectly.
But as the sequence length, $2 grows to 100K or 200K tokens, maintaining that lossless memory becomes just prohibitively expensive in terms of memory bandwidth.
And the industry's response to that has largely been the resurgence of linear RNNs. We've seen models like Mamba 2 or Gated DeltaNet trying to solve this exact issue.
Right, and those models do achieve a constant $0 decode time and linear prefill, which is incredibly appealing for hardware efficiency.
Massively appealing.
But the underlying issue, however, is that they rely on a fixed size hidden state. When you push them to extended contexts, like, say, 128K tokens, you observe a demonstrable degradation in test loss.
Because it just runs out of room.
Basically, yeah.
Yeah.
A fixed capacity state simply saturates. It cannot losslessly compress an arbitrarily long sequence without overwriting vital historical information.
Makes sense. So the overarching goal of this deep dive is to explore how TTT-E2E manages to bridge this gap. We want to understand how it achieves the scaling curve of full attention, but maintains the constant inference latency of an RNN.
Yeah, and to mimic that human-like compression, we clearly have to fundamentally alter what a language model is doing during inference. We have to abandon the assumption of static weights.
Right. The architecture starts as a standard transformer, but it strips out global self-attention entirely, doesn't it?
It does. Instead, it uses sliding window attention, or SWA, for local context. But the profound shift here is the introduction of test time training, or TTT.
So meaning it trains while it's inferencing.
Exactly. As the model processes the input context during inference, it continuously trains itself. It performs next token prediction on the context sequence and actively updates its own weights. It's literally compressing the context into its parameters on the fly.
Okay, I have to push back hard on that premise.
Sure, go for it.
If we take a pre-trained language model and blindly run gradient descent on its weights at test time, which, by the way, sounds suspiciously like the dynamic evaluation methods we saw a few years ago, don't we inevitably trigger a massive distribution shift?
That is the exact failure mode the authors label TTT naive.
Because the initialization of a pre-trained network is absolutely not optimized to be dynamically rewritten during a forward pass.
You hit the nail on the head. If you attempt that with a standard static model, the gradient updates rapidly corrupt the pre-trained feature representations.
It just forgets everything.
Yeah, performance often collapses to a level barely better than a model with no attention mechanism at all. The theoretical breakthrough of this paper is how they prevent that collapse through end-to-end, or E2E, meta-learning.
Okay, I'm going to need you to walk me through the mechanics of that. Because the idea of optimizing a model to be updated later is twisting my intuition a bit. How do you mathematically prepare weights for test time training?
So we have to separate the process into two nested optimization loops. During the actual pre-training phase, which is the outer loop, the objective is to find an optimal set of initial weights. Let's call them $2.
Okay, $2. Got it.
Inside that outer loop, we simulate the inference process. We take a sequence, perform the inner loop of test time training via gradient descent to update $2 and to update it,
Right.
and then we calculate the language modeling loss using those updated weights.
Wait. So the loss function that dictates the primary pre-training updates
Yeah.
is calculated after the simulated test time training has already happened.
Yes, that is the core of bilevel optimization. The outer loop backpropagates through the inner loop's gradient steps. You are literally computing gradients of gradients.
Oh, wow.
The initialization dollars is explicitly forced to learn an internal geometry that is highly receptive to future gradient updates. It learns to learn.
Okay, that is incredibly elegant in theory. But any ML engineer listening to us right now is immediately going to see the computational nightmare here.
Oh, the hardware implications are massive.
Right. If the inner loop is updating the weights via next token prediction, does that mean we are taking a gradient step after every single token? Because an inner loop batch size of $1 means we completely lose the parallel processing power of modern GPUs.
It would take forever.
Yeah, it would take forever to prefill.
Online gradient descent, token by token, is definitely a non-starter for hardware utilization. So the engineering solution is to shift to mini-batch TTT.
Okay, so chunking it.
Exactly. Instead of updating after every token, the sequence is chunked. The authors settle on a mini-batch size of B1 Kähler. The model processes 1,000 tokens in parallel, computes the gradients, and then applies a single update to the weights.
I see how that restores hardware parallelism,
Yeah.
but I'm struggling to see how that preserves the sequence modeling.
How do you mean?
Well, if the weights are frozen for 1,000 tokens, doesn't the model lose the ability to learn from the tokens early in the batch to predict the tokens later in the batch?
You've hit on the architectural flaw the authors call the mini-batch paradox.
Ah, okay.
Within that dollar chunk, the dynamic weights haven't been updated yet. Therefore, for tokens inside the batch, the model essentially functions as a bitogram model, relying solely on its static initialization.
That sounds problematic.
It is. If you plot the token level loss across a single mini-batch, you see a sharp spike as the model attempts to predict token 900 without any compressed memory of token 100.
It's like reading an entire textbook chapter without taking any notes and waiting until the very last page to try and synthesize what you've learned.
That's a great way to put it.
You're inevitably going to forget the beginning of the chapter by the time you reach the end, meaning your comprehension on those last few pages is going to be terrible.
The biological analogy holds up perfectly here, and this is where the sliding window attention mechanism re-enters the picture.
Oh, right, the SWA we mentioned earlier.
Exactly. SWA acts as the short-term working memory buffer. By setting a sliding window size of Hue-A colors, the model maintains a local lossless KV cache that spans across the mini-batch boundaries.
I see. So the SWA bridges the gap. It holds on to the high-fidelity local information just long enough for the MLP weights, which represent the long-term memory, to receive their gradient update at the end of the batch.
Precisely.
But we aren't running test time training on the entire network, are we? I mean, updating a multi-billion parameter model at inference time seems way too heavy, even with mini batches.
Yeah, the paper includes extensive ablations on where to apply the TTT updates to maximize compute efficiency. They found that gradients only need to backpropagate through the final 1/4 of the transformer blocks.
Only the last 25%.
Yeah. The earlier layers are primarily extracting syntactic and lower-level semantic features, which just don't require dynamic adaptation. The actual contextual compression happens in the later layers.
And even within that final quarter of the blocks, I imagine we have to be selective about which parameters get updated.
Absolutely. The embedding layers, the normalization layers, and the SWA projections are strictly frozen during the inner loop.
Because if you update them,
Attempting to update them introduces severe instability into the outer meta-learning loop. The TTT updates are exclusively applied to the multi-layer perceptron, the MLP, inside those final blocks.
okay, but if we are aggressively overriding those MLP layers to compress the current context, how does the model retain the vast amount of world knowledge it gained during pre-training? It seems like catastrophic forgetting is inevitable.
That's a very valid concern. To mitigate catastrophic forgetting, the architecture uses a dual path forward pass in those specific blocks.
Dual path, meaning two parallel streams.
Exactly. They introduce a second, completely static MLP layer that runs in parallel to the dynamic one. The outputs of the dynamic TTT MLP and the static pre-trained MLP are simply added together via a residual connection.
Oh, that's clever.
Yeah, the static pathway preserves the pre-trained world knowledge, while the dynamic pathway handles the fast adaptation to the current context.
That's a fascinating separation of concerns. The model basically has a dedicated structural pipeline for what I already know versus what I'm currently reading.
Right.
To put the scale of this into perspective, we should probably look at how this compares to other recent attempts at this problem, like the TTT-KVD, or key-value binding architecture.
Right, so TTT-KVD was an earlier formulation that tried to use test time training to reconstruct the keys and values layer by layer.
Basically trying to force the weights to act exactly like a KV cache.
Exactly. But TTT-E2E abandons that layer-wise reconstruction entirely. It simplifies the objective to a single end-of-network next token prediction loss.
Which significantly changes the capacity of the hidden state, doesn't it? Because in a 760 million parameter model, the TTT-KVB approach yielded a hidden state of roughly 18 million parameters.
Yeah.
And I think anyone listening will recognize that 18 million is quite small. But what does TTT-E2E achieve?
Because TTT-E2E leverages the standard MLP layers as its dynamic state, the hidden state size explodes to 88 million parameters for that exact same 760 million parameter model class.
Wow, so that's nearly a 5x increase in compression capacity.
Yep. And counterintuitively, you have the prefill latency because you aren't calculating layer-wise reconstruction losses anymore.
So the architectural theory is sound, and the engineering tricks make it viable. But the ultimate test and sequence modeling is empirical scaling. What happens when we push this to scale?
The researchers scaled the TTT-E2E architecture up to a 3 billion parameter model. They train it on 164 billion tokens from the Slim-Pajama and Star-Coder datasets.
Real-world numbers, basically.
Exactly. And the empirical results clearly validate the meta-learning hypothesis. When evaluated at a 128K context length, TTT-E2E maintains the exact same test loss advantage over a full attention transformer as it does at an 8K context.
Wait, really? The scaling curves are perfectly parallel.
Perfectly parallel.
And how did the linear RNN baselines fare under those same conditions?
Not well. Models utilizing hybrid SWA, Mamba 2, and Gated DeltaNet exhibited severe degradation. Their loss delta relative to full attention widens significantly as the sequence length stretches from 8K to 128K.
So TTT-E2E really stands alone here.
Yeah, it stands alone in these benchmarks as the only linear time architecture that tracks the full attention baseline across extended contexts.
But mathematically, this raises a fundamental contradiction, I feel like. We established early on that TTT-E2E is a lossy compression method, whereas full attention is lossless recall. How is a lossy method actively matching or even beating full attention and language modeling perplexity across a massive 128K context?
Yeah.
Where in the sequence is it gaining this mathematical edge?
So the token index breakdown reveals something deeply counterintuitive. The advantage of TTT-E2E does not manifest at the end of the context window where you might expect its compressed memory to shine.
Where is it then?
The performance gains actually emerge on the earlier and middle tokens of the sequence.
That seems entirely backward. Why would dynamic weights be better at predicting the beginning of a document?
It comes down to the optimization constraints placed on the network. Think about the weights of a standard static full attention model.
Okay.
Because those weights are frozen at inference, they must be globally optimized during pre-training to accurately predict all possible future tokens simultaneously, regardless of where they appear in the sequence.
Right.
That is an incredibly rigid, highly constrained optimization landscape.
I see. Because the static weights have to be a jack of all trades for the entire document. Their capacity is diluted. But the TTT-E2E weights are dynamic.
Exactly. The weights of TTT-E2E at any specific index only need to minimize the loss for the current mini-batch. They do not have to carry the mathematical burden of the entire future sequence, because the model inherently relies on the fact that future gradient steps will adapt the weights for those future tokens.
So it only has to worry about what's right in front of it.
Precisely. By hyper-focusing its capacity entirely on the present moment, TTT-E2E achieves lower perplexity on those early tokens, which aggregates into a superior overall test loss.
That fundamentally reframes how we should think about parameter capacity. You're effectively unburdening the network.
You are.
But, any structural deviation from self-attention introduces trade-offs. If we are swapping lossless recall for lossy semantic compression, what specific capabilities break?
The most glaring deficit is exact match retrieval, which we can quantify using the needle in a haystack or NIAH evaluations.
The classic test.
Yeah. If you inject a completely irrelevant random UUID into the middle of a massive textbook, a full attention model will use its KV cache to perfectly retrieve it.
Because the KV cache simply stores the token representations verbatim. completely, regardless of meaning. But I assume TTTE2E struggles to retrieve that UUID.
It fails significantly on random UUID retrieval.
Ouch.
But we have to view that failure through the lens of its objective function. The meta-learning process trains the inner loop to compress semantic contextual meaning that actually aids in predicting the next logical token.
And a random string of characters doesn't do that.
Exactly. A random UUID offers zero semantic value to the surrounding text. The gradient updates effectively treat it as anomalous noise and just discard it from the hidden state.
So for the data scientists and architects listening right now, this creates a hard bifurcation in deployment strategies.
It absolutely does.
If you were building a strict retrieval-augmented generation pipeline, a database querying tool, or say a legal tech application where verbatim exact match recall of arbitrary strings is just non-negotiable, you must deploy a full attention model.
Right, no question.
But if your use case involves synthesizing, reasoning over, or summarizing massive documents, where semantic understanding vastly outweighs rote memorization, TTTE2E offers a much more efficient path.
Recognizing the inherent biases of your architecture's compression mechanism is critical for deployment. You cannot force a semantic compressor to act as a relational database.
Well said. Let's transition to the hardware reality of that deployment, though. Computational efficiency is ultimately what dictates whether these novel architectures survive outside the lab. How do the latency metrics actually look?
For inference, the profile is outstanding. TTTE2E maintains strict over-inference latency per token. When benchmarking a 128K prefill on an H100 GPU, the TTTE2E architecture is 2.7 times faster than an equivalent full attention model.
2.7 times faster. And because it leverages standard MLP layers, it avoids the custom kernel hell that usually plagues linear RNNs.
Oh, yeah, that's a huge point.
You aren't forced to write highly specific CUDA operations just to balance the memory I/O on new silicon. You can shard the hidden state across multiple GPUs using standard distributed training tools, like tensor parallelism.
The inference stack is incredibly standard. However, the major bottleneck and the primary limitation the authors acknowledge lies in the training latency.
Right, there's always a catch.
Calculating gradients of gradients is exceptionally memory intensive.
Because to backpropagate through the outer loop, you have to keep the intermediate activation states of the inner loop in memory.
Yeah. And over a long sequence, that requires heavy gradient checkpointing through time to avoid out-of-memory errors. Consequently, training TTTE2E on an H200 is 3.4 times slower in wall clock time compared to training a full attention model at an 8K context.
3.4 times slower. That's rough. And even though the theoretical FLOPs per token remain similar, you lose the massive hardware optimizations of tools like flash attention, which currently do not support the bi-level optimization required for gradients of gradients.
Exactly. The authors highlight that developing custom attention kernels that support these specific meta-learning gradients is a crucial next step for the systems engineering community.
Are there any workarounds in the meantime?
In the interim, a practical workaround is to initialize the TTTE2E model from a pre-trained standard transformer. By doing so, the highly expensive meta-learning phase only consumes a small fraction of the total pre-training compute budget.
Okay, that makes it a lot more viable. We've covered a tremendous amount of ground here, so let's try to synthesize the core takeaway. Today, we've explored a genuine paradigm shift in sequence modeling. The challenge of long context language modeling is no longer strictly an architectural caching problem or a race to build a more efficient KV cache.
Right.
TTTE2E proves that we can reformulate the bottleneck as a continuous end-to-end meta-learning problem. For the ML practitioners tuning in, this fundamentally challenges the entrenched assumption that inference inherently requires frozen weights.
Yeah, the empirical results demonstrate that dynamic weights, when properly initialized via an outer meta-learning loop, can actually outperform static weights in perplexity.
It's wild to think about.
It is. They do this by focusing their parameter capacity on the local context, relying on future gradient updates to handle the rest of the sequence. It is a calculated trade-off, sacrificing exact match recall to gain powerful semantic synthesis and linear prefill latency.
And as we wrap up, I want to leave you with a really provocative concept to explore, one drawn directly from the author's notes on data quality. Throughout this deep dive, we've analyzed test time training as applied to the input context, the prompt or document fed into the model. But what if a model applied TTT on self-generated tokens?
Oh man, in traditional linear architectures like LSTMs or modern gated RNNs, you have explicit gating mechanisms that protect the hidden state. They learn to block spurious or noisy inputs from corrupting the internal memory. TTT lacks an explicit gate. It just updates based on whatever tokens it processes next.
So imagine a language model that, during its test time inner loop, generates its own intermediate filtering steps, internal summaries, or chain of thought reasoning. If the model performs its gradient updates on those self-generated, highly refined tokens, rather than the raw input, it could actively guard its own hidden state.
It would essentially be self-curating the exact semantic experience it chooses to compress into its dynamic weights.
Exactly. Think about the implications of an LLM talking to itself during inference, purposefully building a stronger, more noise-resilient memory before it ever outputs a final answer to the user. It is no longer just passively reading the context, it is actively studying it. Just like you, sitting in that very first machine learning lecture, aggressively filtering the noise of the room into the compressed intuition that still serves you today.